Thank you very much joining this symposium. Today I want to talk about the ocean bottom detector, which are focusing on the how we can understand the mantle's radiogenic heat. And so I want to start with the what's geoneutrino. So yesterday we heard from Ingrida about the excellent introduction of the what's the geoneutrinos, but I'd like to repeat. So the geoneutrinos comes from the electron antineutrinos from the natural radioactive decays. So as you know, there are a lot of radiogenic the materials in the earth, like uranium, thorium, potassium, like that. And each element has this kind of beta decay, like this. And as you can see, this beta decay has the antineutrino here, and which is called as the geoneutrinos. And this element has geoneutrino, and at the same time, it's produced the heat, and it's the one kind of the Earth's heat driving the Earth's engine. So this is the energy spectrum of this uranium green and sodium yellow and potassium blue. So as we heard from the Ingrida yesterday, that currently we can only measure the geoneutrinos comes from the uranium and sodium because there is the energy threshold of the inverse beta decay, which is the reaction we're using for measuring these antineutrinos. So unfortunately, the understanding potassium is super big issue, understanding Earth, but current technology that we cannot identify and measure the kind of contribution we have from the potassium. So this geoneutrino measurement can be translated to the very interesting outcomes relating to the Earth. That is as you can see, this reaction, decay reaction, that the number of the geoneutrino can be translated into the amount of the uranium, the thorium in the Earth, and which correspond to the radiogenic heat. So this is what the geoneutrino doing as the experiment. And I'd like to mention one thing on this slide, which is the flux. So as you can see, we have a huge amount of the geoneutrino, which is like the 4.1 times 10 to 6 square centimeter per second. It's huge. But I will show you later the experiment result. But what we can measure is like one event per month. Even this the world's largest antineutrino detector, which is common. So this is what we are doing. So this is I like to mention that why the geoneutrinos is very important, because it's kind of the key point to the challenge, that the big question of the Earth. So one is that what is in the mantle. We discussed yesterday about like LLSBP region, what is there. So so many seismological image, the structure and chemical heterogeneities in the mantle, but we don't know the actual situation there. And also how much fuel is left to drive the plate tectonics, because we don't know the details of the balance between the primordial and radiogenic heat, which is driving the Earth. And so in the talk, I use this categorization, that is the low Q, middle Q, high Q, which has a different mantle radiogenic heat. And in the total, the three models has like 10 terawatt, 20 terawatt, and 30 terawatt of the radiogenic heat. So we slightly know well about the continental crust because we can reach, and also there are many kinds of the way to study. And also in compare with the continental crust, the mantle has lots of mystery. Still has lots of mystery. So the geoneutrino is very useful to know that so geoneutrino can directly define the power to drive the Earth's engine. Okay, so we call this kind of the science as a neutrino geoscience. So this slide show you the summary of what's going on and what will happen in the future in this neutrino geoscience. So the bottom side show you that what we can run from the geoneutrino, and the top part shows that what we need to achieve this what we want to know. So we start from we studied this kind of neutrino geoscience from the 2005. That is the Cameron the first measurement of geoneutrino happened, and after that we try to improve the accuracy of the experiment measurement and also modeling. So that is the connection part between the physics society and the geoscience society, and we work together in improving the modeling, understanding what kind of geoneutrino flux we are measuring. So because of this achievement, that we could know that the total radiogenic heat in the Earth, and also like the uranium-thorium ratio. And next target, we want to know that what's the mantle. So to achieve this mantle, so we need the new type of detector, which is the detector in the ocean. So I will talk about this detail in this talk. But it's also I like to mention that what's the next generation beyond the ocean bottom detector. So that is directional sensitive detector. So I will mention this the next slide. But current technology, we cannot measure anything directional information of the neutrino. So we need a new type of technology. So if we can do that, what we can do is identify what the contribution from the crust and the mantle, and also separating the background using the directional information. And this is kind of this community's dream, that is detecting the potassium geoneutrino. So many studies are going on, and we also need a new type detector. Okay, so yeah, the ocean bottom detector, we can call it the breakthrough. That is beyond the modern land-based detector, transforming our vision of this Earth. So as I mentioned before, I'd like to little bit stop at the directional measurement. So what we need is that getting the quick information of the neutron, which remember the neutrino coming direction. So this is a scheme that if we have the anti-neutrino in the exchange radar, this is target of the experiment, and it's attached to the proton, and it has the electron and also neutron, that is the inverse beta decay. So actually, naturally, this neutron remember the direction of the antineutrino, which is showing this diagram that is kinetic energy versus the theta m, that is the angle between the coming direction and the neutron moving direction. So as you can see, like geoneutrino energy region, that is about 3 MeV. So theta n is less than 35 degrees C. So if we can capture this neutron quickly, we can identify what's the direction what's the direction. So we achieved this kind of special exchange radar, which contains the lithium-6 because it has the huge neutron capture cross section, so it quickly can detect a neutron. And we need the new type detector, light collecting detector, because we need a high vertex resolution because we need to identify that these two positions, prompt and the delayed signal, that we can make that the arrow to the neutrino coming direction. So this is what we need. And if we can know that direction, that we can have this kind of information, so we can separate the class contribution and the mantle using this kind of directional information. Okay, so in this next two slides, I'd like to mention about the current experiment, the latest result, which is accepted last week by the GRL. So so what we are doing is that using the entire data, it starts from 2002 and the end of the last year, and this is 5,227 days lifetime. And in this, the entire data set, we have a lot of things. And the top part show you the event rate and also expected reactor neutrinos and also background in terms of the time. So I don't go detail, but after the March 11 earthquake in this Tohoku area, that many of the Japanese reactors shut down, so which allowed us very clear data for the geoneutrino measurement. Because as you can see here, geoneutrino energy region is very low, below the 3 MeV, and it's same is the reaction neutrino because both are the antineutrino. We cannot separate. So that this geoneutrino, the energy is 100% covered by the reaction neutrino. So if it's decreased like that, we can clearly see that the geoneutrino contribution. So what we did is that using the entire data, which has almost half data, is after the 2011, because of this massive data set of the low reactor period, we could do the precise measurement of the uranium and thorium contribution. So this is one of the figure from the paper. Is that this dot show you the data, and this shaded region is the best fit of the data of the geoneutrino contribution from the uranium and thorium. So using this data, we discussed about the radiogenic heat and also the model separation. So this left figure show you that the contour plot of the experiment data, which show you this blue region. And so like more than 5,000 days measurement, the best fit of the geoneutrino contributions is like uranium 117 and thorium 58, and total uranium plus the thorium is 174. And zero signal rejection power is like this, so we could do the separately the uranium thorium contribution using this clear data set. And using this information, we calculated radiogenic heat from each uranium and the thorium and the total. And the data show you that the total radiogenic heat from the uranium thorium is at the 15.4 plus minus 8 terawatt. And this figure shows you that the comparison between the low Q, middle Q, high Q model. And as you can see, that the common data in the different uranium-thorium ratio doesn't match or the high Q model, which is like 30 terawatt radiogenic heat model. So we rejected this high Q model like more than 99.76% if we assume the homogeneous mantle, and also the 97.9% confidence level if the concentrated at the CMB region. So they improved this kind of improvement allowed us to do the distinct spectroscopic contribution of the uranium thorium. So this is the situation. So the ocean bottom detector. So why we are so interested in measuring at the ocean region? So what we are measuring the geoneutrino is that the total contribution from the crust and the mantle. It can be written like the y equal x plus b, and the plot show you that the crust contribution is x-axis, and the observation, which is y equal the y-axis. So together with the other experiments, that we can do this kind of the analysis. So currently the Cameron is measuring, and Borexino stopped last year, and as we saw yesterday, Snow Plus is taking data, so that the 3 places multi-site measurement can constrain the mantle contribution with this kind of the combined analysis. But it's also the crust estimation needs to be accurate, because in the land-based experiment, about 70% of the contribution is the crust. So the ocean bottom detector. So it's located here. It's very close to the x equals 0, because as we know, the oceanic crust is thin and less uranium thorium. So that if we have the 1.5 kiloton ocean bottom detector for 3 years measurement, we can get this kind of data. So that we can see clearly that ocean bottom detector can directly measure the mantle contribution like this. Okay, so motivations. So firstly, as I mentioned before, the direct measurement of the mantle is very important point. So yeah, we need to be far from the crust, because crust is the source of the huge geoneutrinos. So this is the diagram which show you that each experiment positions the antineutrino rate, And also each contributions, it's categorized as the reactor, and green is mantle, and the crust, red is close to the detector, and blue is the global. So ocean bottom detector is the only the position at the ocean side, but the other one is in the on the land waste. So as you can see, the total number of the anti-neutrino is low, but the contribution from the mantle is the 70% if we can measure at in the ocean. And multi-site measurement is very good. The motivation for the solve the mystery of the liquid Earth, because this can be the first detector for mapping the inhomogeneous mantle, because we can measure several points. And also, it should be a multi-disciplinary detector, which is like just we are talking about entire this symposium that we have the connected science motivation, and this kind of detector can have is the source to connect each disciplinary scientific field. Okay, so not so many time left. So the end of this my talk, I'd like to mention about what is the present status and the future of this project. So actually, the measuring in the ocean, this idea itself starts from the 2005 in Hawaii. This detector called the Hano. And the design in itself is the same as the OBD design. And they did a lot of the technical tests and the detector design in this time. But unfortunately, there is not so many progresses until 2019. So in Japan here, we have the working group, the ocean bottom detector project, together with the Jamstek and Tohoku University. And we are working on the technological development, and also the world first measurement in the ocean with the Rixinchi radar. Even if it's very small, it's a technological test. We can done a lot of things. And also, we can measure like muon in the sea. So it should be the input parameter for the future larger size detector. And in this year or next year, we are planning to deploy this kind of small prototype detector into the 1 kilometer depth of the ocean. And then we want to increase the volume to detect the mantle signal. So if we have like 1.5 kiloton detector, which is like 1.5 times of the common detector, we can measure the mantle contribution. So we are doing some kind of detector simulation and also technical development. So this is the simulated energy spectrum. So I don't go details, but what we get is that in this table show you that the number of each events in the 1 year using this 1.5 kiloton detector. So you can see the total of the geoneutrino signal is 8, and then in this 8 we have 5.76 mantle contribution, and then comparing with the signal, the background is like 10 and 6. So it's very competitive, and almost in this the geoneutrino region we have more the signal than the background. But as you can imagine, this is totally different condition for the detector, because it should be like 4 kilometer depth in the ocean to shield the muon contribution. So it will be low temperature, like 2 to 4 degrees C, and a high pressure, that is 40 megapascal. So it's very different from the current detector situation. Okay, so yeah, the Mantle geoneutrino sensitivity we are right here is a like middle cube model. We can measure like 3 years measurement, distinguish, that is 3.5 sigma confidence level. Okay, so briefly show you the current technical development. So as I said, we need the shield for the PMT itself. And we try to use some acrylic thing, but it doesn't work. And also glass shield, we could get the very clean glass. And we are trying to make the larger size to contain like 20-inch PMT. And Rix insulator, it's also very different. And 4 degrees C temperature, actually we can get the better, brighter than the like 20 degrees C, like plus 9%, and transparency doesn't change. So the technological development has been started like that. Okay, summary. So this, for these 2 centuries, we have asked that what is the energy that drives the Earth? And we started to get some information from the geoneutrino measurement that is totally different to understand the Earth. And today, the physics experiment have shown the usefulness of the geoneutrino. And also, in this past 15 years, the interdisciplinary community has furthered its connection. And yes, this neutrino geoscience should be collaboration between geology, physics, and beyond. So truly the ocean bottom detector is our breakthrough to understand the deep Earth. So that the ocean bottom detector's primary goal is to map the mantle, because we can measure several points, and also the constrain the planet's cooling history to understand the Earth's agility. Okay, thank you.